Okay, guys, I think we can start the session. And today we are going to discuss about some points like mapping, how to map a how to map the robot surroundings using SLAM algorithm. Then how to localize the robot in the map, and then how to navigate. Okay, so while setting the autonomous navigation for your mobile robot, uh, we have to include all these things. Okay, yesterday we have discussed about the navigation stack, and the navigation stack is basically the move base. Okay, it's mainly having the node called move base, and in order to autonomously navigate, these move base require map. Then the move base also require the robot pose in the map. Okay, like there is a term called localization. Okay, there is a term called localization. It means that localize means like if you are using your phone, okay, and if you on the GPS, you are actually localizing your phone or your position in the Google map. Okay, you can localize your position on Google map, right? So for an autonomous robot, the localization means the same thing here. The robot can be indoor robot, outdoor robot. It can have GPS, it can have other sensor for localization. So the robot will have a map, okay, that can we can actually build it, and then after building the map, the robot has to localize on the map. Okay, so that is actually required for the move base. Okay, so the move base is dependent on map and also a thing called AMCL. MCL stands for Adaptive Monte Carlo Localization. It's a localization algorithm. So essentially, the idea is for working with MoveBase, we should enable, or we should start the AMCL node, and we should also start the map server, which is giving the map to the MoveBase. So the question is how to create the map and how to configure the localization. Okay, so first we can check how to create the map. Okay, so that is the first problem. Like if there is a robot with lidar or depth sensor or any sensor, like mostly lidar and depth sensor, if the robot is configured like this, how to create the map of the robot surrounding. Okay, and the objective of creating the map is navigation. Okay, like we can only navigate if we have a map, right? Similar to the Google Maps, like we are using Google Map for A to B navigation. Okay, so same thing, but here we are actually creating the map. Okay, so that technique is called mapping algorithms. So I just want to show you one mapping algorithm. Okay, already implemented algorithm. It's called fast slam. Okay, so if you search for fast slam, you will get the paper. Okay, so just a second. Yeah, I think it's a fast slam. Just a sec. Here, yeah, maybe I can share the link. So essentially, the G mapping is actually a package in ROS. Okay, and this package is actually using a library called OpenSlam. Okay, OpenSlam is the implementation of this FastSlam and all. Okay, so this library is having the implementation of this SLAM algorithm, and SLAM stands for simultaneous localization and mapping. Okay, so if simultaneous localization and mapping. So what is this algorithm about? This algorithm, if you run this algorithm on your robot, it can simultaneously localize them in the map and then also it can map. Okay, so we are using one of the SLAM algorithm. There are many SLAM implementation, and there are many SLAM algorithm. So one of the very popular algorithm is fast SLAM. Okay, fast SLAM. So the G mapping is an implementation of fast SLAM. Okay, so when you run the G mapping package, when you run the nodes inside the G mapping package, the output will be map. Okay, output will be map, and also that is the main output. So here, if you just check the G mapping package, what you can find is there is a node inside this G mapping called slam G mapping. Okay, and what this node does is that this node will subscribe to the scan data. Okay, that is the laser scan data, and then it's also subscribed to the transform of the robot. Okay, and what it publishes is the map. Okay, so if you give the input scan and TF, it will output the map, or it will publish the map. Okay, so this is what the G mapping about. And G mapping algorithm, it's an algorithm, so we can configure that algorithm by setting the parameters. Okay, so basically just understand that inside the G mapping package there is a node. Okay, this node is actually this node is actually subscribing to scan data and TF, and it is publishing the map. Okay, so this is actually the G mapping package, also called SLAM G mapping. So we are going to see how to work with the SLAM G mapping package. Okay, yeah, so that is the first thing that we have to try. Okay, so just understand the working of G mapping package. Okay, its input is scan and output is map. Okay, and so when you put the robot and when you start this node, is that enough for creating the map? Actually, no. Okay, so what we have to do is we have to move the robot after running this node. Okay, so if you move the robot after running this node, what will happen is it will get new scan, and it will actually create the map when it moves. Okay, so maybe I think it will be better to show you the demo. Okay, then I will explain. So let me check with Turtleboard. Turtleboard simulation. Okay, so let me start the Turtleboard simulation. Okay, oh, Turtleboard world. Okay, so we have started the Turtleboard simulation, and then we have to start a launch file from the bring up. Is called remote, which is starting the robot state publisher for publishing the TF, and then let me start the mapping. So for mapping in Turtleboard 3 there is a package called SLAM. Okay, and inside the SLAM there is a Turtleboard SLAM. And yeah, I think you can set the SLAM method, but let's just execute this first. Oh, just a second. Let me start the SLAM. So it's started the SLAM algorithm. So you guys can see, right? Here, what you can see is the scan data that is shown as green, okay? And the simulation is here, okay? And what happening is that in SLAM algorithm, when you execute any SLAM algorithm, okay, here we are trying the G mapping, and if you are working with Turtleboard 3 stack, it is having different SLAM algorithm, okay? So now we have to move the robot. So how can we move the robot? We can use maybe keyboard teleop, or like the Turtleboard, it's actually coming up with some package for teleoperation. Let me see if there is any. Yeah, there is a package called teleop, and inside that there is a Turtleboard teleop key. Just a second. So I'm going to do the teleop, meaning I'm moving the robot manually, okay, using the keyboard. So now using the W, you can see the keys, okay, W, A, S, D, X, okay. If you press W, the robot will move forward, okay. So if you just release a key also, the robot will move forward. If you press S, it will stop, okay. So just observe the map, okay, just observe the map. So while moving the robot, the map is getting updated, okay, the map is getting updated. And then, so what will happen if you move the robot around? The robot will, the SLAM will be like creating a full map, right? So this was the map that we have seen in the navigation. Okay, yesterday we have tried the navigation, right? So after doing the mapping from the G mapping or from a SLAM algorithm, we have to save this map and then we can use it for navigation. So if you simply drive the robot around, okay, if you simply drive the robot around, what you can find is you are literally creating the map of the environment, okay. So you can find it's almost finished. So the gray color, no, the gray color is actually indicating that there is no obstacle, okay, there is no obstacle. And you have to note that the robot should not be, it will not be drive in a very high speed, okay, because these algorithms are like not very perfect. So there should be like a medium speed or like minimum speed, so that the map building also will be perfect or accurate, okay. So here what you can see is the obstacle. The black color indicates the obstacle, okay. The black color is actually indicates the obstacle, and the gray color indicate there is no obstacle in that. And here are the obstacles on the center, okay. So what we have done was we have started the simulation of Turtleboard, then we have started the SLAM launch file, then we have started the teleoperation, okay. So now it seems like the mapping is almost done, right, almost completed. So now we can save the map, okay, we can save the map. So using this command, ROS run map server map saver -f test turtle. So what happening is that there is a package called map server in ROS. Inside that there is a node called map saver, okay. So if you run this node with a file name, okay, then what happening is that this node will be subscribing to map topic, okay, and save it as a PGM file, okay, it's a image file. So you can see it is waiting for the map, receive the map, then writing the map, and you can able to see the file, the map is actually stored here. Okay, this is a saved map. Okay, this is a saved map, and there is a configuration file. So in this configuration file, it is like it's a configuration file for the map. So there is a name of the map, then the resolution, then origin. Okay, so if you don't want to, I mean, you don't need to change it anyway. Sometime we need to change the origin, but this is fine. Okay, so this is the output of SLAM algorithm. Okay, SLAM algorithm. And basically what is SLAM, what we have done was we simply run this node called SLAM G mapping. Okay, that is all. That's all we have done. Okay, so maybe we can check the Turtleboard 3 package called Turtleboard SLAM. Okay, so if you are creating your own robot stack, so you have to give a you have to create a package called Turtleboard 3 SLAM. I mean, the name has to change. The name of your robot _ SLAM, and inside that, actually, we have to write a launch file. So here, what they did was, there are different mapping algorithm. So one is G mapping, one is cartographer, one is Hector, then Carto, and it's actually an exploration algorithm. Okay, so this launch file can work with multiple SLAM algorithms. Okay, by default it is actually taking G mapping. Okay, so in this launch file you can able to see there is an argument called SLAM method. The default value is G mapping, and then based on that the name of the SLAM method, it is launching a launch file. Okay, launching Turtleboard 3 _ gmapping.launch. So that launch file is actually here. Okay, so basically this is the launch file we are loading. Okay, this is the launch file. So here you can see SLAM G mapping. We are basically starting the SLAM G mapping node. Okay, and we are passing these set of parameters. Okay, there are many parameters actually. So the main parameters are like the SLAM G mapping node has to know the base footprint, which is the base frame of the robot, and which is the ODOM frame of the robot, and which is a map frame. Okay, so if there is any changes in the name, like if you are giving base footprint as world or something, then you have to change the name here. Okay, and all this parameter now, the G mapping parameters are putting in a config file. Okay, that is this. So here you can see if you are checking the G mapping wiki page, you can find many parameters. Okay, these are the parameters of that node, and these parameters are configured inside this YAML file. Okay, and whenever this node starts, whenever this G mapping launch file start, it will load those YAML file parameters. Okay, so basically in order to create a map of the robot environment, what we have to do is we have to run SLAM G mapping node with all these configuration parameters. Okay, so make sure you are publishing the scan data and also the TF data. Okay, so this is the mapping. Okay, so I will explain the configuration later. So this is a basic understanding. Okay, so using SLAM G mapping, or many other SLAM algorithms are there, like cartographer, Hector, all SLAM algorithms are using in different application. but commonly for indoor robots we are mainly using gmapping. Okay, so all these packages are available and we just need to like start these nodes and give these parameters. So it's basically about configurations. Okay, basically all configuration. Yes. So this is the first step that we have to do before the navigation. Okay, first we have to map the environment. So once we map, we will get the map file, right? We will get the map file, okay, which is the output of the SlamG mapping. Okay, and now what we require is configuring the navigation stack and configuring the localization. Okay, so here is the algorithm that we are using for localizing the robot on the map. So I think you got the understanding like what is localization, okay, and why it is important. So imagine you are using Google Maps. Okay, you are using Google Map, and you are driving a car and you are using your phone to navigate. What happens if the GPS signal is lost? What happened? Then we don't know where are we in the map. Where is our location in the map, right? So that is what we are calling like we lost the localization or we lost the position. Okay, so if lost the position, then we don't know where is our position with respect to the Google Map. Okay, the same situation can happen for the robot because using the SLAM algorithm, we have created the map. Then the next role is to navigate on the map. So for navigation, the robot has to know its position, right? So how will it understand its position, current position? For getting the current position, maybe we can use GPS or we can use laser scan or some other sensor to locate itself on the map. So this is a very important part of the navigation. Otherwise, we can't able to reach the destination. We don't know the current position, right? So that is what the localization. Okay, so there are many algorithms available for localization. So one of the popular algorithm is AMCL, which is actually helping us to localize the robot using laser scan. Okay, using laser scan. So again, if you check the AMCL package, what you can get is like you can see the subscribed topics. Okay, so what it is taking is it is taking the scan data, okay, and it is subscribing to TF, it is subscribing to map because it require the map, right? Require the map. And also sometime what happening is that when we start the robot, one limitation, I will say it is one limitation, like yeah, when we start the map, I think maybe I can just show you that situation. So I'm starting the simulation. Okay, let it start. Okay, so we started the simulation. Okay, and now we are like starting the robot state publisher, and now we are starting the navigation. Okay, navigation. Oh, wait. Yeah. Yeah, we don't need to start that remote. Yeah. So just check this situation. So we just started the robot. Okay. And when you start the navigation launch file, it is starting what? It is starting move base, AMCL node to localize, and map server, which is actually publishing the map file as a topic. Okay, so here what is happening? You can identify, right? the simulated robot position is here. Okay, the simulated robot position or actual robot position is here, but where is the localized robot? It's actually on the center, right? So this is what one limitation of the AMCL. The limitation is that we have to give the initial position of the robot. Okay, sometime it can find it out by simply rotating. So if you just simply rotate the robot, it may find it. But commonly what you have to do is there is an option called 2D pose estimate. Okay, 2D pose estimate. So we have to click this button and give the initial position of the robot. Like you can give the initial position as here. So you can see it is matching. The laser scan is matching with the obstacle, meaning it's mostly here. Okay, mostly on this location. Okay, and you can also see lot of particles. Okay, lot of particles around this robot. That is called AMCL particles. Okay, it's called AMCL particles. So here you can see, right, it's actually see, this is actually the AMCL particle. So in order to visualize AMCL particle, you can add this pose array display type. Okay, pose array display type. And so what is this particle? So you can see a lot of particles, right? I mean, the particle is surrounded on the robot. So what is happening is that lot of particles means less accurate is the robot position or localized position. Okay, less particles mean more accurate the robot position with respect to the map or in the map. Okay, so if you are driving the robot or like if you are just giving a goal position, initially if you are finding a lot of particles, then at this time the robot position is not very accurate. Okay, but what happen if we give a goal position? Okay, so in this scenario I will advise you to rotate the robot manually or give a goal position. Okay, give a goal position. So then the situation will change. See, when the robot start moving, then the AMCL will start working. Okay, the AMCL start working, and see, the points or like the particles is actually reducing. Okay, reducing means the robot position with respect to the map is getting accurate. Okay, but still there are particles, but it will not be zero. It will be like some value, but you can find that the particles are like getting reduced. Okay, it is very less compared to the initial position, right? So this is what AMCL gives to us. So if you check, AMCL is subscribing to scan, TF, then the initial pose is what we are giving from the ROS. Okay, and then the map topic, and the published values are the pose of the robot, then the particle cloud, that is what we have visualized, and the TF. Okay, so basically the AMCL can publish the TF from map to ODOM. Okay, so here when we have the map, the fixed frame will be map. Okay, in order to find the fixed frame, I will advise you to check the RQT. You can take the RQT and then you can visualize the TF3. So you can find map is the top one. Okay, with respect to the map, we are having ODOM. Okay, so just check this thing. I don't know whether you have observed this. So map to ODOM. Okay, so where, I mean, with respect to the map, where is the odometry frame? That is actually publishing by what? The AMCL node. So that is what it is showing, broadcaster. So if you remember the TF concept, there is a broadcaster node, there is a listener node, right? So the broadcaster is what? Broadcasting the TF. Okay, so the map to ODOM is broadcasting by AMCL. Okay, and ODOM to base footprint is actually broadcasting by the Gazebo plugin. Okay, Gazebo differential drive plugin. Okay, in Turtleboard 3 they are using Gazebo differential drive plugin. And other thing like base footprint, base link, all the things are actually the part of URDF. So that is actually publishing by robot state publisher. Okay, so this is how the TF tree work. And the TF tree is very important because while creating the navigation package for your robot, you have to get this TF tree correct. If you are not getting the TF tree correctly, that means there is some problem with the configuration. Okay, so the importance of AMCL is that. Okay, and also you can visualize the nodes. Okay, just visualize the node, just a second. Node graph. Yeah, so you can identify, right? So here we have the move base. Okay, we have Gazebo here, and so the move base is subscribing to map topic, and there is a node called map server. Okay, there is a node called map server. So that is actually publishing the map file as a topic. Okay, and we have the AMCL which is publishing TF, and we have Gazebo that is also publishing TF, and also the robot state is also contributing the TF. Okay, and what is the output of the move base? I think we have discussed this yesterday. Like move base is outputting command velocity. Okay, so that will be going to Gazebo because we are doing the simulation now. So this is what happening in the background. There are 1, 2, 3, 4, 5 nodes. Okay, the move base is the main node which is actually doing the navigation and all the things. The AMCL is working for broadcasting the TF between map and ODOM. Then the map server is publishing the map topic. Okay, and the Gazebo is like subscribing to command velocity, and the robot state publisher is contributing to the TF. Okay, so this is what happening in the background. Okay, so this is with the topics, so it will be, yeah, so this is having the topic as well. So move base is here, then map server is publishing map topic, then Gazebo is publishing the scan data, and Gazebo is subscribing the command velocity from move base. Then only the robot will move. Then Gazebo is also publishing the odometry, which is subscribing by move base. Okay, and yeah, so this much things are running in the background. Okay, so if you check the AMCL is subscribing to the initial pose, and it is outputting or publishing the particle cloud and then TF. Okay, so this much things are going on in the background while navigation, while we implementing the navigation. Okay, so that is an abstract idea about the mapping and localization of the robot. So basically we have to configure all these nodes, the G mapping node for mapping, then move base and AMCL node for navigation. Okay, so let me know if you have any questions. So after this we can discuss we can take one standard robot and then we can discuss the packages. Okay, and I will also send one repository, like one symbol repository, which is having a differential drive robot and also having the navigation stack, mapping and everything. Okay, so I will send a reference. So as of now we are very used with the Turtleboard 3, right? So we can use the Turtleboard 3 packages for explaining the navigation stack. Um, so how to configure the navigation stack? So because I'm using the Turtleboard 3 package, because it is having lot of stuff, in the sense, if you are planning to work with a different SLAM algorithm, there are different options. So if you want to create your own packages or simulation, I think Turtleboard 3 stack will be very useful. Okay, so so let's start with the Turtleboard 3 simulation, and also how to configure the SLAM and navigation package. Okay, so before that, let me know if you have any doubt. Yeah, so let me know, guys, like if you have any confusion so far. Any confusion, guys? Because while discussing ROS concept, I think this is one of the popular concept, like ROS navigation. Okay, so this thing, the topics that we are discussing is very abstract. I mean, currently we are only discussing the abstract, but the detailed things, the configuration, the fine tuning will be like discussing in the upcoming chapters. But this is actually the very basic stuff. Okay, so this is the Turtleboard 3 documentation, and it is having the tutorial for setting the Turtleboard 3 world, and also running the SLAM navigation and everything. So if you want to try, I will recommend you to try the simulation and creation of map and navigation. Okay, after that you can work with the code. Okay, so that is what my suggestion. Okay, okay, so if you don't have any question, then I'm just going to the packages in detail. So I mentioned that we are focusing on like creating differential drive robot simulation, and then we are implementing the SLAM and navigation on the top of it. Okay, so that is the agenda. So in order to create simulation, we have to create the description file, description package, and then we have to create a gazebo package which is having the launch files, all this stuff. Okay, so while working with Turtleboard, we are using this launch file. Okay, so this launch file, when you launch this file from Turtleboard 3 gazebo, it is loading a world file. Okay, it is we are getting a world file, right? Maybe I can show you that. What I am mentioning is this world file. Okay, so this is actually a world file. Okay, I mentioned that like in gazebo, everything around the robot is world, and you can actually create a world for the robot. So the world file is actually the SDF file, simulation description format. So that file can be saved as .world. So here in Turtleboard, if you can check, they are actually giving a world file already. So if you just go to Turtleboard 3 gazebo, and if you go to the world folder, you can see different world file. Okay, so here is our world file. So basically, if you open this world file, you can see the SDF file. Okay, so this world file having set of models. So there is sun, there is ground plane, then there is a Turtleboard 3 world. It's actually a model actually. So in gazebo we have models, right? We have models, and I think I have explained that before. So in the world file, we are loading different models into the world. Okay, so in the world file, you can see we are loading different models, and the Turtleboard 3 guys actually created a model called Turtleboard 3 world. Okay, so that is actually loading in this world. Okay, so the individual components of a world is called models. Okay, so in this folder now, there is a model folder, and you can find the models that is given by Turtleboard 3. So Turtleboard 3 world. So this is how a model package looks like. It's not a package, like it is having some configuration, like it is having an SDF file. So this is what Gazebo model looks like. Okay, you can create your own Gazebo model. Basically, the Gazebo model is a SDF file. SDF file is very similar to the URDF, which is having joins and link. Okay, so if you want to create a Gazebo model which is having links or joins, you can create like this template. Okay, you can simply copy paste and change the SDF file. That will work. Okay, so essentially, if you start this simulation, we are creating a world, and all the other stuff like the plugins and everything is actually there in the description package. Okay, so we have the description package here, and in the description we have the URDF, and you can find Turtleboard 3 different Sacro files. Okay, so we have burger, then waffle. These are the two models of Turtleboard 3, and we have, this is the Sacro file for burger, and this is its Gazebo definitions, Gazebo plugins. So if you check it, you can find the Gazebo related tags, the ROS diff drive. Okay, so this is what the diff drive plugin that we have seen in the Gazebo website. So they are not using the ROS controller, but they are using the Gazebo plugin for implementing the differential drive, and they have an IMU. Okay, so the IMU plugin they have loaded, and they have laser scan. Okay, laser plugin is loaded. Okay, so this much of plugins are loaded in this simulation. Okay, so you can able to like go through this and then just get an idea. Okay, that will be great. So this is the method that we learn from each repository, because this is one repository, and you can check Husky, or like there are many mobile robot simulation and navigation implementation. So you can go through it and find how they implement all this stuff. Okay, so in order to set up the navigation for Turtleboard 3, there are two repositories. Okay, so the instructions for setting up is all given here, but I can mention the idea. So, and also it will work with different ROS version. So mostly, like if you working in Noitic, just change to Noitic, and yeah, then you will get the updated instructions. Okay, for simulation there is a tab here. So in order to work with the simulation, yeah, Kasim, can you hear me? Maybe yeah. Do you have any questions?
Sorry, I just joined
Okay,
this.
okay.
Sometime
Maybe
this
you can just mute then. Okay. Yeah. So the instructions for like setting the simulation, and yeah, all this stuff is mentioned in this page. Okay, so you can simply try it, and there are two models of Turtleboard, right? Waffle, and so you have to set up the Turtleboard 3 model before starting it, and yeah. So basically, maybe I can quickly show you how to set up the packages for Turtleboard. So maybe I can create a workspace. Just a second. So I'm creating a repository. By the way, let me check the packages. Okay. So the packages are already there. We have installed the packages. So what I will do is I will uninstall all the binary packages. The problem with the binary packages are like the we can't edit it. Okay, we can't edit it. There are some problems, I mean, can happen. So what I will do is I will simply remove all these binary packages. Okay, just a second. And after removing it, I will show you how to set up from the source code. Okay, so this is one reference that we can follow for working with your own mobile robot. Just a second. Yeah, we are removing it, and in the meantime what I will do is I will create a workspace called turtlebot 3 workspace, and I need to create an src folder inside that, so you can use this syntax. So there will be an src folder, and then the steps are like simply clone this repository, that is turtlebot 3. Okay, I'm just sharing it. So let me just copy paste the link and git clone turtlebot 3. And also there is a separate repository for the simulation. They have created the simulation package in a separate repository. That is not I mean recommended, but you can maybe able to do that so that you can isolate the hardware packages and simulation. So currently it is updating. So we have removed the binary packages. So let me clone all the turtlebot 3 packages. Okay, yes, now we have to clone the simulation packages on the same folder. Okay, okay, after that simply do the catkin make and fix the dependency. So I'm just doing the catkin make, and let's see what will happen. Okay, so there is an error, like it is complaining about could not find the package configuration by turtlebot 3 messages. Okay, so it couldn't find the turtlebot 3 messages. So what I will do is I will just go to the turtlebot profile, okay, and just search for messages. Okay, so why they put it as independent package? Because this is actually I mean the messages can be used anywhere. You can use it for simulation, you can use it for hardware. Okay, so they actually put it as independent. Okay, you can use this package for publishing these kind of messages. Okay, so what I'm doing is I'm simply cloning these messages into the workspace and then doing the catkin make again. So it is building. Let's see. Okay, so I think there is okay, got it. Yeah, so there is an error, mostly because of the gazebo version. So it is complaining about could not find a configuration file package for Ignition Common 3 graphics. So let me check that package in Synaptic. I don't know, like they have changed something. Okay, so the package is there, but it's already installed, but I don't know why it is not detecting. Let me check the repository, like whether is there any Noitic Yeah, there is a Noetic Devil. And I think better will be like following the instruction from the documentation. So they will have the exact documentation. Seems like, okay. So you can see the change difference, guys. See, they are actually cloning the Noetic branch, okay, instead of the master branch. So that was one difference that we have done. So here also there is a Noetic Devil. Okay, so what you have to do is we just clone the repository, right? 3 repository. So you can find Turtleboard 3 simulation, Turtleboard 3 and Turtleboard 3 messages. So just go to Turtleboard 3 simulation and then do a git branch. So you can see it is master branch. So you have to check out to Noetic Devil. Okay, Noetic means the ROS version and Devil means development. So this is the branch that we require. Okay, so now it is checked out to Noetic. The same for Turtleboard. Okay, 3. And just check the branch and now you have to check out to Noetic Devil. Okay, so now it seems like it is compatible with Noetic, and do the catkin make. Because the master branch, no, the master branch will have some updates, so that may not be compatible with Noetic. So currently, like, it seems like it's building properly. Okay, so this thing you have to note. Okay, just wait for some time. I think it will build. Yeah, seems like it will. Yeah, it actually builds successfully. Okay, so what is the next step? You have to source it, right? So this is the source command, source Turtleboard 3 workspace. This indicate home folder. Okay, so inside the home folder there is a workspace, devel and setup.bash. Okay, so just copy this line into .bashrc. Okay, and then paste it here. Okay, Control O, save, and then you can check for the packages. Turtleboard 3 packages is here. Okay, so you can see the Turtleboard 3 gazebo is on the workspace. Okay, so it's all set. We can start the simulation. So the simulation, yeah, the same launch file. Just a sec. Let's see whether it is showing the world. Yes. Okay, so what we have done was we are loading the simulation from the source code, not from the binaries. Okay, so far we have used the Synaptic Package Manager and installed the Turtleboard 3 binary packages, but now we have installed the packages from source code. Okay, and it's ready to go. Okay, and so now let's see the navigation package and all. Okay, I can give you an idea about all this stuff. Okay, so just go to the source code. So we have Turtleboard 3 navigation, okay, package, and in this package actually the main thing is configuring MoveBase and AMCL. Okay, so if you check the navigation.launch, this is the launch file that we launching for the navigation. So I can give you an abstract idea of this launch file. So basically this launch file launches the necessary things for starting the navigation. Okay, so what are the things that is required for navigation? Maybe I can take the navigation stack diagram. So this is the diagram that we are discussing, right? Yes. So in order to start the navigation, we need map server, okay, which is actually a node that is already present in ROS. The map server is publishing the map. Okay, we need that. Then we need the sensor topic. So which is publishing that? Gazebo. Okay, so when you start the simulation, we will get it. And then we need the AMCL node, right? Then who is publishing the TF? I mean, TF is publishing by AMCL, then Gazebo, and also the robot state publisher. And who is publishing the order? Gazebo. Okay, and who is giving the goal position? It's ROS. Okay, and what is left? We have to start move base, right? Okay, so now if you check the launch file, you can understand. Here we are starting the basically we are starting there is a launch file called turtlebot 3 remote, which is basically starting a robot state publisher. So you can simply see here in the launch file remote. Okay, so what it does is that it will start robot state publisher, and it will also like parse the URDF. Okay, so this is the thing that basically it is starting the robot state publisher. Okay, so the robot state publisher help you to publish the TF from the URDF. Okay, and next you can see the map server. Okay, what is the purpose of map server? The map server is what publishing the map file. Okay, I can show you a demo. I can individually run the map server. So I think we have created a map of turtlebot, right? This is the map. So in order to publish this map file, what you have to do is you have to run a node called map server, and then you can give the map file name .yml. I think this will work. Just a second. Yeah, read. Okay, yes. So what is the output, guys? So we have started the map server. Okay, map server is a node, and if you give the map file, okay, if you give the map file .yml, what will happen is that it will load the map, and then it will publish what? It will publish the map topic. Okay, so if you just do the ROS topic info, you can see it is publishing by map server. Okay, and this map can be visualized in ROS. Okay, so if you just add the map, you can see the map that is publishing by map server. Okay, so that is what the map server does. So the argument of the map server is the map file. Okay, so this is a default map file. We can actually change it, and then we are starting AMCL. Okay, in a launch file we are starting the AMCL, we are starting move base, and then we are starting ROS. Okay, so this is the important part of navigation. Okay, so if you just go to the navigation package, you can see the amcl.launch file. So basically the amcl.launch having it's actually starting the node called AMCL. Okay, from the package called AMCL. Okay, it is actually inside the package called AMCL, and the node name is AMCL. Then the name also giving us AMCL, and these all things are the parameters. Okay, so we have to give the scan topic, then the initial position. If you want to set an initial position, by default you can set it. So this is the configuration of AMCL. I mean, basically in this launch file we are only starting one node, that's it. Okay, and what is happening in move base, we are only starting one node. Okay, but the thing is we are loading tons of parameters. Okay, so here you can see we are only starting one node, which is move base. Okay, but MoveBase require tons of parameters. What are the parameters for? There is local planner, global planner, local cost map, global cost map, and recovery behavior. Okay, and also the parameters for the MoveBase. Okay, that parameters are loading here. Okay, so these parameter has to load to MoveBase itself. Okay, because all this plugin, no, these all plugin are part of MoveBase. Okay, so you can see the cost map, some common parameters, then local cost map parameter, global cost map parameters, MoveBase parameters, DWA local planner. Okay, all these parameters are here on the param folder. Okay, so if you check if you check base local planner, you can see the configuration of a planner and its properties, and properties of cost map. Okay, then global cost map parameters. Okay, so all these parameter, no, so if you check the ROS navigation, if you take this link, basically you can see there is a there are some local planners already available called DWA. There is a global planner already available. I mean, these all are some default planners available. Okay, there is MoveBase package, then there is rotate recovery. I mean, all these things are the default one. So if you take that wiki page, you can find the parameters of that. Okay, so if you check the DWA parameter, these all are the parameters that we can configure. If you check the global planner, you can see a set of parameters. Yeah, here these are the parameters. Okay, but you don't need to worry. Actually, you can actually take the some default parameters, and that will work in most of the scenario. So this is for the rotate and recovery behavior. Okay, plugin. So these parameters are here. Okay, so if you're working with navigation stack, the most difficult thing is the configuration of these parameters. Okay, but luckily, like if you can use these same parameters for any robot, mostly it will work. Okay, mostly it will work. Slightly it needs some adjustment, that's it. Okay, so you can see different configurations of these modules inside MoveBase. Okay, and yeah, so this is what the MoveBase or the navigation stack is about. The navigation stack is about configuring these parameters. Okay, and these parameters, like if you check the cost map common parameters, you can able to see like the inflation radius. Okay, I think I have mentioned about inflation. That is the extra layer that we have to that we are giving for the real obstacle. And there is observation sources. So currently we are observing through scan topic. Okay, so all these things, no, all these things is actually mentioned in the wiki page. Okay, we can't explain all these parameter. Okay, but all these things it is actually available. So configuration of these parameters is the navigation stack. Okay, and also for the SLAM, if you check, is basically the configuration of the gmapping node. Okay, gmap. So basically, if you check, if you are talking about the navigation stack, it's basically the configuration. There is no programming. Okay, there is no programming. I will say zero programming, and with all I mean setting all these configurations. Okay, so in this session I will not plan to like discuss deep about on the configuration parameters, but just an idea how to set up a robot navigation stack and I mean work on it. Okay, so I think we can just conclude here. Okay, and then I will be like putting some projects idea this week to work on, so you can actually take the projects idea from the list and start implementing. Or if you have your own idea, you can work on it. Okay, so that is what we are doing in the upcoming weeks, and we will be completely focusing on the projects. Okay, if I have any reference material I need to share, I will share. Okay, so I will mention you if there is any class coming, so I will take it. Otherwise we have to completely focus on projects, and you can ask doubts in the project idea channel. Just a second. ROS answers channel. Okay, so you can ask questions in this channel. Okay, so I will guide you. Okay, so let me know if you have any confusion. Like, I was trying to give an idea about like Turtleboard 3 robot and its packages, how to configure the navigation stack. And so after this session, it will be great if you can configure the navigation stack. I mean, not navigation stack, just run the simulation and run the navigation, play with it. Okay, and then let me know if you are facing any issues. Okay, so let me know if you have any question so far. Okay, uh, let me know.
Hi, sir.
Hi Kulchit.
Uh, so for projects, are we supposed to use this Turtlebot repository and modify it according to our like the project that we are making
Yeah, so
and
yeah,
just do it?
yeah, so I think I will recommend you you to or you guys to start by modifying the existing one. Okay, initially, then we can start our own, like we can create our own simulation. Then we can configure our own navigation package and all. So currently we are just learning, right? So rather than like immediately implementing everything, we can simply learn from some existing works. Okay, not only Turtlebot 3, there are many references. Okay, Husky, then and we are not only focusing on mobile robot. We have the simulations of robotic arm. So we are not directly jumping into navigation. We have to implement some good simulations. Okay, so you can actually start playing with some existing simulations of different robots. Then you can implement your own robot by writing URDF and creating a simulation of that URDF, and then after that you can plan to work with the navigation stack. So this is the plan. So we just missed the projects like from Turtle Sim. We have actually worked with some projects in Turtle Sim. After that we didn't do any other projects. So we are planning to do a set of projects from the URDF. Okay, Kuljit?
Okay,
Yeah,
sir.
yeah. Any more questions?
Sir, some of the classes were missed. So it would be great if we can have like a reference handy. It would be very helpful to know which classes would be for review before starting on the
Yeah,
projects.
yeah. So Kalpesh, I think I have added all the classes. I mean, the recordings are already there. So if you miss anything, I think you can simply catch it up, because currently we are focusing only on the project. So all these videos, no, all these videos are like updated. It's all recorded. Okay, so
Yes, sir.
yeah, so you can simply watch all this stuff, and then we are starting doing projects from, I think, from um, yeah, from the URDF. Okay, from the URDF concept we are starting doing projects. So if you have doubts, you can post it in the ROS answers channel. Yeah, so anyway, I will give reference. Okay, there are simple references, there are complex references, so I will actually share all these things. Okay, no worries.
Thank you, sir.
Okay, okay. Okay, guys. Then I think I will update today's video on GitHub soon, and then we can start doing projects. So I will share the project's idea, and how we can proceed. Okay. Okay, guys. Thanks for attending. So now we will not have classes, but we will be interacting with Discord, and sometime we can arrange some meeting, like project meeting or something, in between, and then we can discuss. Okay. Okay. Okay, everyone. So good night, and then keep in touch in Discord. Okay. Bye.